Alright, time for the next set of problems from this review page. Number 6 says to calculate the acceleration of a speedboat that can go from 0 meters per second to 60 meters per second. That's a change in velocity. And since we seem to be increasing our velocity, I'm going to make sure that we use a positive number when we solve the problem. It takes 9 seconds for that to happen. Our acceleration formula is change in velocity divided by time. So from 0 meters per second to 60 meters per second, that is an increase of 60 meters per second. The time it takes for that to happen is 9 seconds. So 60 meters per second divided by 9 seconds, grab your calculator, 60 divided by 9 equals 6.7 meters per second squared. The meters per second tells me I'm increasing my velocity every second. 6.7 meters per second per second. The meters per second squared part is just a label. It's a unit. Don't look at that exponent and think you've got to square any numbers. You don't. That would be ridiculous. Number 7. Calculate the acceleration of a semi-truck on cruise control at 55 miles per hour. So, if I'm going 55 miles per hour, the cruise control is a device in your vehicle that limits your change in velocity to 0. So I'm not speeding up or slowing down. I'm going 55 miles per hour the entire time. So as long as I'm going straight, since my acceleration is change in velocity over time, and my change in velocity is 0, and time could be anything, let's call it 1 hour, because I don't know what it is, it's still 0 miles per hour. Left off my label here, 0 miles per hour. Alright, nothing too bad. Uniform circular motion, that's anything that has a constant speed and a constant change of direction. So if we put you in a car in the parking lot and we had you moving at 5 miles per hour and we turned your steering wheel 20 degrees to the left and we locked both of those in place and we just let you go in a circle, that would be uniform circular motion. A clock has uniform circular motion. Matter of fact, a clock also has what's called periodic motion. Periodic motion is any repeating motion. An example of something that experiences this: a clock, a swing set. Assuming you don't have any health issues, your heart, those sorts of things. The difference between Earth's rotation and revolution we talked about last time. Remember, rotation is when the Earth spins on its axis like this, and this causes day and night. You turn towards the sun over here, and you can see it. You turn away from the sun and you can't see it, it's nighttime. Revolution is when the Earth goes around the sun. We have the Earth way out here with its little axis, it's north and south, and it works its way around the sun over here, goes around the sun again, and this causes seasons. Here where the northern hemisphere is pointed towards the sun, that's summer. Over here where the northern hemisphere is pointed away from the sun, that is winter. So the difference between rotation and revolution, and what do they each cause the observer on Earth to experience? We experience day and night because of rotation, and seasons because of revolution. Which one has a greater speed, Earth's rotation or revolution? This one happens more frequently. It only takes a day for us to rotate, but the distance is pretty small, 25,000 miles. It's not too much compared to revolution. Sure, it takes us a whole year to get around the sun, but we're talking a lot greater distance. So our revolution is faster. We've got to make sure that when we think about faster, we're thinking about meters per second, not just time. You know, in a track event, they tell you who's faster just by giving you a time value. It's not really accurate. It'd be better if they gave you the meters you've run divided by the time. But they don't listen to me, so yet. When I take over. Never mind. If a rock is being twirled in circular motion, so you're in the backyard and you've got a string, a little rock on the string, and it's spinning around. Everybody wants a rock to wind a piece of string around. And you're spinning it around there, and suddenly the string is cut. So it's going along in its motion, and boom. What will happen to the rock? The rock is going to fly off in a direction tangent to the circle. Tangent just means it touches the circle. It doesn't follow the radius outward. It continues its forward motion, and since it's no longer being pulled towards the center, that's the direction the rock goes. Same thing would happen if gravity stopped and we had the sun here, the earth would fly off that direction. Don't worry about it, it's not going to happen, you're going to be fine. Despite what Mr. Armitage may tell you next door, it's not going to happen today. Boom. Flipping over to the next side. Get ready. Get psyched. Because this side is all about slope. And it's not that slope is that much tougher than the rest of it, but this tends to be the part that people screw up the most. Position versus time graph. That's meters and seconds. So a line on here would have a slope of rise over run, or meters over second. And what do we measure in meters per second? Velocity. We could say speed as well, but because I can tell positive or negative from my slope, I get a direction, so velocity is more accurate. A speed versus time graph, we've typically drawn these with this sort of deal, where I've got positive meters over seconds here, positive meters over seconds here, and then seconds of time. Slope here, I have meters per second per second. That's my rise. I run a second. So meters per second, or meters per second squared, is acceleration. The dot diagram, remember that's like the oil drop from the back of my old Buick. Something moving along at a constant speed, we have the same number of meters every second. Right? The spacing will be even. An object running at constant speed means we're just going to cover more meters per second, but they're still going to be uniform because we're constant. Something with a positive acceleration, that means we start out slow and we work our way towards fast. So a little few meters per second, few meters per second, few meters per second, few. Whoa, look at that, it's incredible. I love it. And an object going with negative acceleration. Negative acceleration means we are reducing our meters per second. So I start out with a lot of meters per second, and then I get fewer meters per second. Each dot happens at a second. The space between them goes down. So, what does negative velocity mean? Negative meters per second means that I am losing meters. I'm going backwards. We've also called that towards the origin. Remember, that just means the starting point. Wherever you started your run, we're going back towards it. Negative position, well, think about it in terms of a racetrack. Here's 0 meters. There's our 1 meter mark, 2 meter mark, 3 meter mark, 4 meter mark. What would it mean if I had negative 1, negative 2, negative 3? That would just mean I'm behind the starting line. Behind the origin is another way to say that. Every time Mr. Skirmahorn runs a race, he has to start several meters behind just to make it fair for everyone else. You know, he still wins, but you know how it is. The man's an animal. Negative acceleration. Oh, we saw that. Negative acceleration. That means losing meters per second or slowing down. So take a minute, double check those things, and we'll move on to the last part.